Dear students, today we will talk about Kepler's third law of planetary motion. I have already introduced you the Kepler's first and second law of planetary motion. Today we are going to do the last, that is Kepler's third law of planetary motion. It states that the square of the time period of revolution of a planet around sun is proportional to cube of semi-major axis. Semi-major axis. I have told you that the planets revolve around the sun in elliptical orbits, and in case of an elliptical orbit there is a major axis and a minor axis. Half of the major axis is called semi-major axis, it is denoted by A, and half of the minor axis is called semi-minor axis, and that is denoted by B, right? Now, you have also learnt about the differential equation of motion for an object moving under the influence of a central force, and that equation was d square y by d theta square plus y is equal to 0. And we know that for such kind of a differential equation, the solution is given by y is equal to a cos theta. I don't need to go into details, you know this. For y, we had made a substitution that this is equal to u minus mc by j square, where u was simply a substitution for 1 by r, right? So for this y, that is a cos theta, we are recapitulating certain things, was equal to 1 by r minus mc by j square. So this 1 by r was how much? Mc by j square, then it was taken common, plus aj square by mc cos theta. I don't need to do it in detail, you have already done it in the previous video. So then we had recognized this equation with the equation of conics. So that was 1 by r is equal to 1 by L, where L is the length of the conic section, right? And for 1 by L, we are actually substituting mc by j square plus into 1 plus epsilon cos theta, where this epsilon is called the eccentricity of the orbit. And obviously, aj square by mc has been substituted by E, and mc by j square was substituted by 1 by L, right? Now, if you are recapitulating all this, then today we can proceed to the Kepler's third law, right? Now, as per the Kepler's second law, we know that aerial velocity of a planet moving around the sun is constant. That is, the radius vector which joins the planet with the sun sweeps equal areas in equal intervals of time. We have already done that. We have done its derivation as well. So we had learned in the previous video that aerial velocity dA by dt was constant. And what was that? J by 2m, where J is the angular velocity of the planet, this angular momentum, and m was the mass. Now we can integrate it. So dA is integral j by 2m dt, right? So this comes out to be A is equal to j by 2m t. Now what is the area of the ellipse? You know it from your knowledge of mathematics that it is pi AB, where A is the semi-major axis, B is the semi-minor axis, and this is pi. So this is equal to j by 2m. In third law, what are we going to do? We are basically arriving to find the time period of the rotation of the planet around the sun. So we are basically interested in time period of revolution, right? So t is equal to 2 pi m a b by j, right? From here we can write that since t is equal to 2 pi m a b by j, so square of t is 4 pi square m square a square b square by j square. Now there is also a relation that connects the semi-major axis with the semi-minor axis, and that is b is equal to a times 1 minus epsilon square. I hope all of you are aware of it from your knowledge of mathematics, that the semi-minor axis is a times, that is semi-major axis, 1 minus epsilon square, where E is the eccentricity of the orbit. Now for this b, we will substitute this equation, that is d square is equal to 4 pi square m square a square. For b, I can write this a square 1 minus epsilon square divided by j square. So this is equal to 4 pi square m square. Now this is a 4 1 minus epsilon square divided by j square. Now, we know this 1 by r, this was equal to how much? 1 by L, this equation, 1 by L, 1 plus E cos theta, right? If we have to find the maximum and minimum value of this 1 by r, obviously that will be determined by the value of cos theta. And we know that the value of cos theta ranges from +1 to -1. Therefore, from here we can take it to next page, that 1 by r maximum value will be 1 by L 1 plus E, because we know the maximum value of cos theta is 1. Now if we take the reciprocal, obviously it will give us R minimum. So that will be L 1 plus E, 1 by 1 plus E, right? Now what is this L? This L is j square by mc. So R min is j square by mc 1 by 1 plus E. Similarly, we can find R max. R max will be j square by mc 1 by 1 minus E, because at that time the value of cos theta will be minimum, and that is how much? That is -1. So it will be 1 minus epsilon. And in this way we can arrive at our maximum will be j square by mc 1 by 1 minus E. Now you are also able to comprehend that for a planet moving around the sun, suppose sun is placed here at this focus, when the planet is nearest to the sun, this is the distance, and when the planet is farthest from the sun, this is the distance. Obviously, the sum of the two distances is equal to the length of the major axis, and the length of the major axis is 2a. So we can write that radius r max plus r min is basically how much? Is 2a, isn't it? Because 2a is the length of the semi-major axis. Obviously, this is going to be the sum of the two distances when the planet will be farthest from sun and when it will be nearest to sun, right? So let us add it up. So 2a will be equal to r max plus r min, and that is j square by mc will be taken common, and this will be 1 by 1 plus E plus 1 by 1 minus E. So that will be j square by mc. In the denominator, it will get multiplied. That will be a square minus b square, 1 minus epsilon square. Here it will be this and this will go. 1 plus 1 will be 2. That 2 will get cancelled with this 2. So at the end of the day, you are left with a is equal to j square by mc 1 by 1 minus epsilon square. And you can substitute this a back in this equation, right? So you can substitute it here, and what do we get? You get that t square is equal to 4 pi square m square. Here you have a4 for one of the a's. So we'll write a cube into a. For one of the a, we will write this. That is j square by mc 1 by 1 plus e square. What other factors do we have? So we have one more j square. So let us see what do we get at the end. So j square and j square goes, right? M and M will go, right? So what else are you left with? Yes, we have also this 1 minus e square, right? So you have 1 minus e square term also here. So finally you are left with 4 pi square m a cube by c, right? So one of the m goes with this. You are left with 4 pi square only, right? J square goes with this. 1 minus epsilon square goes with this. So you are left with this term only. In this term, you can find that 4 pi m c, they are all constants. So square of the time period of revolution of the planet around the sun is actually proportional to cube of semi-major axis, right? So this is all about the Kepler's third law of planetary motion. But then you can ask me a question which I should expect from you as beginners in physics, as the students of first semester, right? that if we had arrived already at an expression of a4, what made us to manipulate this equation and finally arrive at a cube? What convinces us that the square of time period of revolution is proportional to cube of semi-major axis and not the fourth power? Why didn't we stop here? All I mean to say that. Why didn't we stop here? The answer is that whatever theories and mathematics we do in physics, that needs to be supported by experimentation. Because when we observe the planetary motion experimentally, we can find that square of the time period of revolution is basically proportional to cube and not to fourth power and not to fifth power, right? Therefore, this is the reason that we further go on to manipulate the equation to arrive at a more proper result that matches our experimental observations as well. And we do it numerous times in physics. For example, I can give you a simple example that power, electric power, is V into I. But at the same time, we know that this voltage is IR. It is current into resistance, so it is I square R also. So how are you going to decide whether power is proportional to the first power of I or to the second power of I? This is through experimentation. These kinds of conflicts are resolved by experiments. Similarly, when we have arrived at an equation which shows that square of time period of revolution of the planet around the sun should be proportional to the fourth power of, we did not stop because our experimental observations do not confirm to this statement. They rather confirm to this statement. Therefore, we further modify the equation and reach to this result. And this is something that is in conformity with our observations in cosmos, right? Similarly, at a more elementary level, I gave you this kind of an example, and there are scores of other examples in which you have to decide by virtue of experiment, by virtue of observation, that which equation is likely going to be the true equation, right? So that's all about Kepler's third law of planetary motion. And in the subsequent video, we will be doing certain numerical problems about these laws. That's all.